In this video, we want to look at the result of the two models that we made in the previous video. The one that we made the model 3D, and then when we added the salinity to the model. So I close this. I have my quick plot open here. I will go and try to open the files that I had. I will first open also the results of delta 2 as a base of comparison. Then I will open the results of delta 3, which was our 3D model. And after that, I will also open the results of delta 4, which is the model that we add salinity to. Delta 4. So now they are loading. And now I can look at it. First, I'm going to look at delta 2, which was the result that we had from before. And I will change the time to morphodynamic time, morphological time. And I look at the final bathymetry of the delta that was made in this model. I can go bed level in water level points and look at it. So you can see that this was what we saw before with mud and sand. In 2D, delta was developing like that. I will go to delta 3, our 3D model, and I changed again the time to morphodynamic time, close, and I look at the same time the morphology that was developed in this model, and you can see that they are pretty different. So when we make the model 2D in depth average mode and a 3D model, you can see that the results are quite a bit different. I also can go to the model number 4, which we added salinity. Again, I change the time to morphodynamic time and look at it, and now you also can see that even this is a bit more different than the others. You can see that all of them are the same time. The boundary conditions were exactly the same. The difference here is that in the middle one we had a 3D model, and in the right panel we had the model that was 3D and also included the salinity. So you can see that in all three the delta is developed, but because of the different processes that we took into account, the results are different. But now we can also take a closer look to what is happening, especially in these two models. Let me close this, this, and this. Now I'm going to look at the model number 3, so delta 3, which was our 3D model. And I want to look at cross-section in the middle of the model in this direction. So for example, cross-section number 51. And what I want to look into this is the velocity first. So if I open the velocity, now we have the 3D velocity here. So I can find the velocity. I'm looking at the magnitude of the velocity, and I'm looking at the time 10 time step, which is pretty at the beginning of the simulations. So if I now look at it, you can see that the velocity is coming in from the river. Of course, the water is coming in with a velocity of maximum about 1 meter per second. But if you look carefully, you can also see a profile that is generated in the because we have 3D model in depth. There's a profile of velocity. Closer to the bed, the velocity is smaller, and when you go up, the velocity gets higher and higher. And you can see that this is the beginning of the model. But when the model, the evolution has continued, for example, if I move further in time, you can see that the canals are developed, and inside this channel, we have more and more velocity, even more than 1.2 meter, but also there are some places that the velocity is low. But again, you can see that there's a profile of velocity when we move from bottom to top. So we can look at the velocities in 3D as well. The other interesting thing that we can look at here is actually sediment concentrations. For example, the mud concentration. If I look at the mud concentration very early in the simulation, for example, time step of 2, then I can see this. So the mud concentration is almost uniformly in depth is coming to the sea and moving towards the deeper areas. You can see that. But at the same time, if I look at sediment sand, you can see that this is concentration is really high when we are looking at the bottom. So closer to the bed, the concentration is higher. And this, of course, logical because sand is bigger and then it can be suspended less than the mud and cohesive sediment. And the other thing is that we had forced the model to bring zero point 0.2 kilogram per meter per, sorry, we have forced the model to bring zero point 0.2 kilogram per cubic meter of concentration of mud from the boundary inside. Yeah. And then we can see how it has moved through the model. And then if I continue like for some to see some other times, for example, if I move it further, you can see that the concentration in the main channel of the mud is still pretty high and it is more or less constant in the depth. However, in the deeper sea, we don't see much mud. And if I move also the one for the sand further in time, more or less at the same time, you can see that again, very, very close to the bottom in the main channels, we have very high concentration of the sand because that's a place that sand moves as a sort of a bed load and it cannot be suspended and remain in water for a long time. So you can see that the behavior of the uh, sand and mud is very different when we look at it in a 3D way. And that has of course, the effect of the morphological development that we were seeing in the model, and the resulting delta formation is somewhat different when we take the 3D processes into account as well. Now you can yourself, you can look into the other things of the model and try to see different things. But what the other things that I can show you here is also I can look at the top layer of the water and look at the sediment concentration for mud. Yeah. So if I move this to sediment mud, I can look at the sediment concentration and you can see that the sediment that comes from the river is now expanding into the model or diffusing into the model. And if I move further, you can see that this mud on the top layer of water is being dispersed and moving there. But if now look at the same thing for the sand, and if I say quick view, now on the top layer, we hardly have any sand at the beginning of the simulation. And if we move also further in time, again in the top layer of the uh, water, we don't have a lot of concentration of the sand. You can see this is maximum of 0.06 kilogram per cubic meter comparing to what's happening in mud with more than zero point 0.2 kilogram per cubic meter. It is very, very low concentration. But for the now, if I close this and I only look at the sand now, and it time, for example, 50, if I look at it at the top layer, you can see that the top layer concentration of sand is very, very small. You can see that. And if I look at the bottom layer for the same time, if I look at the bottom layer concentration of sand, you can see that this is now much, much higher. Yeah, so it goes up more than zero point 0.2 kilogram per cubic meter. So concentration of the sand closer to bed is much higher than at the water surface. So these are also different things that you can take into account, or you can look and see and you can use the result of the model to analyze it. The other interesting thing that maybe we should look into, we can go to delta 4, which we had the salinity, and we again look at the cross section there, cross section number 51, and we look at now the salinity there. So at the beginning of the model, if I look at time step number 2, I can see that the fresh water with salinity of 0 that comes in from the river is now moving in the sea. Again, on the top layers, you can see they're moving much faster than the lower layer. And we can see some sort of a saline water wedge here. Of course, if the number of the layers in vertical direction was more than 5, we could see this better. But again, you can see this to some extent, this saline water wedge. And then if we move in time, we can see also that because of the amount of water with salinity of 0 that's coming from the river, the delta itself is becoming more and more fresh water. But when we move from delta towards the sea, again the salinity is increasing. And again, we have a stratification of the salinity, especially in the sea at this time. Lower, close to the bottom, we have the saline water, and top, the salinity is going to be lower and lower. Again, if I go till the end of the simulation, again, delta is more developed to the sea. The water in the delta, again, have very low salinity, but when we get to the sea, the salinity increasing and increasing. Another thing which is interesting to see here is if I look at the salinity at the time step of 2 for layer number 1, which is the top layer, I can say quick view, and then you can see at the top layer we have the extension of the salinity and freshwater differences. So freshwater is coming from the river to the sea, and you can see very nicely is dispersing in the sea. And at the same time, if I look at the layer close to the bed, you can see the salinity there looks different because the closer to the bed, the salinity cannot move as fast because of the wedge of the saline water that we have there. Now, if we move also further in time, for example, if I come here, you can see that on the top layer, this saline fresh water is dispersed quite a bit, and you can see the influence of it all over the model. But for the more or less the same time, on the bottom layer, the salinity or the fresh water is still confined with the wedge of the saline water in delta. So these also interesting things that you can take a look in the result of the model. Now you have seen a few examples of different processes in the model, how to add them and how to look at the results. Now it's your turn to try to look into these results or make your own models and compare the results and give us a report about these comparison. For example, you can look into different percentages of the mud coming from the river, or you can look into the different gradient of the salinity between water in the river and in the sea, and try to simulate different simulations and compare the results and identify the effect of these changes that you have made